Hello everyone. Today I wanted to discuss about the programming and a bit more in depth about air handling unit. I've received a few messages to elaborate about the program for Alerton Visio. I just thought I'll make a general introduction on the air handling unit. Before that, I'd like everyone to like and share and subscribe so that I can make more videos, so it will be uh, more sharing of knowledge, what I understand. Okay, without further ado, let's get started. We have the air handling unit. We have the general typical schematic for air handling unit. We have the controller here. Consider this could be anything from Siemens, Schneider, Honeywell, Alerton, Trend, Distech, whatever controller this could be. We have the air handling unit here. As you can see, we have this pressure sensor, and it's a typical system arrangement with VAVs. And you have the supply fan, return fan, obviously with the variable frequency drives adjusted to run at a certain frequency depending on the VAV arrangement, and which will ramp up and down the speed of the supply fan so as to maintain the static pressure 1.1, 1.2 inches per column, whatever is set or adjusted as per the consultant requirements. You have the hot water coil, chill water coil, heating coil, cooling coil. You have the outdoor air damper, mixed air damper, exhaust air damper, and the damper actuator. It could be anything from Honeywell controllers. You have the Bray actuators, or you have the actuators from Honeywell. And then you have flow station, flow meter, return fan, and this is your area or the space which needs to be controlled and regulated. So based on this, we have the AHU diagram here. I have the program, Visio program. So I'll just go a bit more like this is our Visio standard page, and we have, if you can see here, the fan stop, and we have the first program strategy. What we do is whenever we are designing or getting into the programming, what we have here, we want to make sure we have all the inputs, outputs, the points list with us. We need to have the IO point list so as we can design the program. We need the strategy and the approved consultant design. We need that with us so that we can design the program as per the required approved program for this particular site. What I say on the BMS, even when I was in England, we were told that everything is based on site specific conditions and site specific requirements. So no two sites, no two job sites have to be similar. There are always some kind of modifications or changes. So it always has to be site specific requirement. On the basis of site specific requirements, we design the program. So for the fan start stop, we have the first thing for the fans. The page we are doing is, you want to make sure, just zoom in a little bit, so you have, and just first thing you want to make sure we have the command. We make sure the command is enabled. So for the occupied command, that's the first condition. So if we have the occupied command BV40 and Alerton, and we have the status of that command BV64, if that is enabled, that is the first thing which we focus on. And then we have certain safety conditions. Supply fan flow switch, we want to make sure the supply fan flow switch, again you see there's input number 9, so it's a hardwired point. It is a current status. It could be the switch. We need to make sure that this is enabled, and there's a delay on break. DOB is a delay on break. So once the command is given, again we take this BB point, binary value. It's an software point, and we have used the negate condition here, and then we move on further to the SR set reset flip-flop, and we have the BV26 output going to the supply fan alarm. So what we are doing here is, if we have given the command here, and after the delay and the command, if we have the supply fan relay command and the status. So once we give this command and the status doesn't turn on, then we generate the supply fan fail alarm. So what we are doing here is we are creating an alarm condition. That is, if we have enabled the fan, you have given the binary output. Now this is a relay, it's a binary output 0, what we have taken here. We have given delay on make. So once we have the supply fan start relay enabled, 20 seconds, and then you don't have the status of the fan. If the fan is not running, so due to whatever, so many issues we find is, if the fan is not running, if the motor is bad, if the fan belt has gone bad, so all these alarm conditions. And if the fan doesn't turn on, then we give and generate the supply fan fail alarm. So same time we have the fan alarm reset condition. So that is what we have given here, is a fan alarm reset point. So BV20 is a reset point on the software page of the BMS graphics. So if you press BV20 software point, that resets the alarm. No matter where the condition is, that will reset it. Next is, these points are important, so we need to make sure these are standard Alerton points. Occupied status, we want to make sure, again, BV67, that is, we have initiated the program. Warm-up command, cooldown command, manual disable, and low limit alarm and high duct pressure. So these are the basic conditions which you have entered here. Occupied status, warm-up command, cooldown, manual disable, low limit alarm, high duct pressure, and filter alarm set point. So based on this, there's an OR gate. We have taken a 6 input 1 output OR gate. What it does is, we have these conditions, and if these conditions are all satisfied, there's no alarm. And if the manual disable command is not turned on, and if all these conditions are met, then we have the enable command for the supply fan. So you can see here that supply fan relay, basically binary output 0, that's our hardwired output command, and that gives the supply fan relay. So we have these software point conditions again. So this is the first program we are writing so as to have a safe enable of the fan command. So that turns on the fan, and what you see here are these runtime accumulators. So what we're doing here is, we are creating, these are software points. So you have the runtime hours. Basically what these accumulator software points are doing is, they are actually calculating the number of hours which the fan is run. Same thing with the filter. So based on the filter alarm, every 3000 hours or whatever set point, then that alarm will turn on. So basically BV21 will give us the filter alarm, AV82 is a fan runtime. So this is BV21 is again a binary alarm. The filter alarm is basically enabled or disabled. So if the hours are calculated here, this is the comparator. Suppose you have put in 3000 hours of the set point, and if the fan has run more than 3000 hours, and if it exceeds, so this is plus minus, so once it exceeds, it gives an alarm. So I'll show you what this comparator does. Anytime you want to check what these software modules are doing, you have a help menu here, and once you click on it, it gives you the complete description of what that module is doing. So basically what this does is compare two analog inputs and produce a binary output as the result of comparison. So what it does is, if you have a plus input greater than the minus input, plus trigger dead band, plus input less than or equal to minus input minus the restore dead band, and then if there's no change, and so these conditions you can meet. So basically the output will be on when the plus input is greater than or equal to the minus input, plus the trigger dead band, and the output will go off when the plus input is less than or equal to the minus input. So what it means is, if you have 3000 hours set point, and if it runs more than 3000 hours, if it's 3001, 3002, or it's equal, then it will generate a filter alarm. Once you reset it and this goes to 0, then the BB21 turns off. That is an indication of the filter alarm basically. And then you have the filter alarm set point is here. Yeah, so basically what it does is, so this is giving us indications on the program itself, like when to have the filter alarm, filter changed, or if it's a fan alarm. So this is how the general page will look like. And this is the first fan start stop command. So basically what we are doing here for the fan start stop, we want to make sure that the fan command is on, and then the fan command is on, and then you have the fan flow switch, which indicates that the fan is working. Sometimes if you have a motor which is kind of stuck, it's not moving, and then that results in heating up of the system of the motor as well, and that could result in unfavorable results. So to avoid all these, we have the fan flow switch and the fan command and the fan alarm reset, so as to make sure that there's no issues with the fan operation. And then you have our low limit alarm, high duct pressure. This alarm, basically what we're doing here, if you notice on the high duct pressure limit, if the ducts and the VAV suddenly close and the fan is running at 60 hertz, then if someone has put it on manual 60 hertz, or that could cause the duct to be compromised. You don't want the ducts to get compromised and break out in the seams and have leakages, because that could cause structural issues and you will have loss of airflow and you're not going to meet the static pressure set point. So that is why you have the high pressure limit, and that is what we're doing here to make sure that the initial start of the fan is satisfactory initiated. The whole AHU is satisfactorily started. And then you have the next page, what we have programmed is the pressure fan. And so what we're doing here, I'll show you again. So this is our AHU, typical AHU over here. And supply fan, what we did is, this is the program we were just writing on, supply fan. So what we have done here is the supply fan start conditions. We made sure that the fan was running, there were no alarms, the fan status was good, there was no high duct pressure issues, and then the fan VFD gets enabled and it starts and it ramps up to a certain frequency, whatever is set at based on the duct pressure sensor. If you have a duct pressure sensor, it will have a set point and it will maintain that static pressure in the duct. Okay, so back to the program. So over here, this is the pressure. So basically, what we are discussing is the pressure set point and the adjustments. I'll show you what we do here based on this. So supply fan relay, we want to make sure a supply fan is on. So what we have taken directly command. So we want to make sure. So basically what this switch does is, whenever the control is initiated, like this is the condition for the fan to be enabled. Once the fan is enabled and you have on and off is 0, so whatever the fan speed response based on the PI loop, I'll show that in a minute. So that status is going to keep and give the output AO0, analog output 0, gives us the frequency of the fan. So over here you can see supply fan flow proof. So that's the indication that the fan is running and the fan status is on. You have the PI loop tuning constant, as I mentioned in our BMS programming. We are using the PI, proportional integral only. We're not using the proportional integral derivative loops. If you read the controls basic by Norman S. Neese, the author of the controls, you will understand that we use the PI loop most commonly. So the tuning constant we have kept it as 5, and the current supply set point and the feedback. So this thing I will explain to you a bit more. So what is this is PI loop. What we have here is the proportional integral KP, KI proportional integral constants, SP is set point, feedback is our input, I max, I limit, and STUP. And this is the PI and this is the output. So you see the frequency, we are trying to tune it down. So basically it indicates on the module itself. So always we start with the sequence number, make sure it's a unique sequence number, you're not copying the sequence number, and you have to make sure you have to have this sequence number always, you see this is 600, so this has to be more than 600 because this is the next in line. So that once this finishes, then we take the 610. That's how the program runs. KP, proportional integral constants, set point, feedback. Set point is again an AV value, because if you want 1.1 inches of water column, that is what the feedback will try to maintain to have a stable response. I max, I limit 60, 50 have taken. STUP 30, BR0 is our branch. We have taken negate. So that means if it's 1, it's going to be, I mean, whatever the value is, suppose this is an analog value of 48, then it's going to give us 52. So that's how this works. I'm going to show it to you in a minute. Let's show you what these things are, just so that you understand. This is the proportional output. We take proportional integral plus 50, where P is KPE and I equal to I previous plus I increment. This is the formula we have to understand. Output is proportional integral 50 plus 50, and P is KPE and I is equal to I previous plus I increment. So basically inputs or feedback, typically a space temperature or a pressure. In this case, we have a pressure gauge 1.1 inches. We want to maintain. Set point is what we want this pressure of the fan. Proportional constant, integral constant, KPKI as I mentioned, maximum integral change, IMX, integral sort of STUP, and integral limit ILMT. The output of the function can be expressed as P plus I plus 50, where P is the proportional component, I is the integral component. Each of these is calculated as indicated below. Note that error is an intermediate variable equal to phase the feedback minus set point, and this is the formula. Okay, so just to kind of give you an idea what Alerton Software Visio does. So okay, back to the program. I'm going to show you what we have here. Okay, so this program basically, so this is all this program is doing. We want to make sure the output of the supply fan frequency, the frequency drives could be from ABB, they could be drives from any company, Danfoss, anything. So these things will remain the same. What we want to do is maintain the set. The primary goal of this program is to maintain the fan speed at a specified set point, so that it has the exact design. It meets the exact design requirements of the duct and its entire length of the duct and the VAVs it's controlling. We want to make sure that none of the ducts are compromised, and you have a correct amount of airflow, maximum CFM that AHU is generating. We want to make sure we're not over or under calculating and designing, so that some areas will have high airflow, some area will have low airflow. Most of the time in places which are old and haven't been calibrated and balanced for more than 2, 3, 4 years, for whatever reason, those places you will have complaints from the tenants and the people who are using that space, that this space is not getting any airflow, it's too hot, too cold, so many factors, so many reasons will be there. All those will have to be looked into and addressed to have a comfortable space. The primary goal why we are doing this is, number 1, safety, number 2, having the right amount of air, and we want to make sure the space temperatures are maintained. So that is what we are trying to do here. So this page is the second page. What we have here is the pressure and the fan page. So basically that's what we are doing here. And then the third page, I'm going to do this page, and then in the next video I'll take the 4th and 5th and so on, the strategy. So what we're doing here in the supply temperature control signal, supply airflow proof. So what we are doing in this strategy is we want to make sure the supply temperature control signal, how much of the temperature control signal you want to maintain. So as I think the reason we are using this is to control the cooling valve, so as to have the right cooling valve control. Okay, again I'll show you what we're doing here, so it'll be easier. So once we have the supply airflow proof, temperature control, proportional constant, integral. So this is like going more into the in-depth of the design. We are using the control parameters here to have a supply temperature control signal and control temperature set point, return supply air temperature, supply fan command, all these things and we are generating a supply temperature control signal. Again, a PI loop, we have used KPKI, set point feedback, and the max limit min and the STUP. So cooling valve control is another page. What we're doing here is controlling the cooling valve. How much of cooling valve, if it's 0 to 10 volt DC, 2 to 10 volt DC, we want to control the cooling valve. And why I'm saying in percentage, because it's the modulating, so you can see we have an AO, analog output, cooling valve control. So what we're doing here is two input scaler we are using. So what this does is, if the input is 0, that's 2 volt DC. If it's 100, it's 10 volt DC. So this is how you can understand. So this is what this particular module is doing. It's a 2-point linear scaler. I'll show you the thing here. Say input is 32, output is 0, and input is 212, output is 100. So basically converting Fahrenheit to, it's an example given, converting Fahrenheit to centigrade. You can use that. In our case, what we are doing is we want to make sure, if you have, because our output is 2 to 10 volt DC actuator, I can tell here, that's our output. And x1, x2, it's a linear x and y axis. So 20 to 100, 0 to 10 volt DC signal relates to 2 to 10 volt DC on the actuator. So we are having a right amount of signal, and that's our output AO2. That's the amount of percentage of actuator you want it to be open or closed. That's what we are doing here. So I'll show you it. So we have values here. So if it's 0, so you can see it's corresponding to 22 volt DC. It could be off. The cooling valve actuator is closed. If it's 100, it's fully open. Right now we are having 47.2. So that's the 4.7 volt DC signal that will correspond to on the cooling valve actuator. Okay, and this is the position of the cooling valve. Eventually you also have, we are taking the status, and we have the position of the cooling valve also here explained. Supply temperature control signal. So right now we're getting 73 degrees. So that's a two linear input scaler. So you can see 60 to 100, and that's what we are controlling. Cooling valve speed. So the speed at which the cooling valve position is moving. Chill water request is on. What we have here is a comparator. If the chill water request is more than 10%, so you want the chill water to be on, so we're comparing it. So right now the chill water cooling requirement is 34% and minimum is 10, so obviously plus is greater than minus, so we have a chill water request. If this request is off, then this cooling valve will not work and correspond to the chill water opening. We have conditions of leak. We don't want the system to be leaking, so this is a leak condition, and that's the supply temperature control signal here. Right, so what we're doing here is, and also we have one more comparator condition. What we're doing here is set point 25, and if the supply temperature is less than 50, is now 50, so low temperature in coil. So basically the coil temperature, we don't want it to get too cold so as to have buildup of frost or ice. So we have a set point. If it goes below 25 Fahrenheit, we don't want the coil to get frost or too cold or ice buildup. So if this is on, then the chill water coil will never be operating. If it gets too cold, even if it's too cold outside or in that particular space, if it falls below 25, then the chill water coil will be closed. You don't want the pipes to freeze and water pipe burst or something, so you don't want those things. And the last page, I'll continue because one more page. It's the heating valve actuator and the heating valve. So what we have again with the heating thing, we have the fan status and there's no leak in the system, and then we have the KPKI constants, proportional integral constants, and this is the hot water supply modulating. And what we want here is the hot water or steam valve signal base. So yeah, what we have here So the steam valve, as we're continuing, steam valve opens and closes based on the set point, and the signal we have, and we open the steam valve or the hot water valve as per the required signal to maintain the space temperature. So this is the basic program for the AHU. We have, as you can see, we make sure that the air handling unit is discharging the right set points. There's no issues with the fan. So as I mentioned, the alarm condition of the fan, we make sure there's no issues with the fan. The fan is running. We have the status. We don't have any high pressure issues, and we have the right amount of set point maintained. There's no compromise in the VAV and the duct system. And then we also make sure the VAVs are controlling the space temperatures based on the set points on that particular space. And then we have the heating coil and the cooling coil modulate and control the space temperature, the supply temperature. We make sure we don't have any cold air, fresh air if you want. Basically, you fully open the outside air damper, you have fresh air introduced. And if you want to have a mixture, 50% fresh air, and you exhaust of 50% and you have a mix 50%, because there are 3 actuators, so you have the control option. Also the strategy, you can control the opening and closing of the exhaust, mixed and outer air dampers to have the right amount of mix in the space. So this is a typical air handling unit program seen in Alerton Visio. I hope this was a bit in depth from my previous videos. I'll continue to make programs on different conditions. You program fresh air handling unit, 100% fresh air for surgical rooms, and different types of filters we use, and what we want to program based on the sequence of operation. And I'll continue making these videos, so hope this helps everyone. If you have any questions, please write to me in the comment section. I'll try to share as much as I know. I'm not an expert, never claim to be an expert. I try my best to learn as I go and proceed, and also at the same time share whatever little knowledge I have to the people, so that to the freshers or young people or people coming from different fields, or just a general knowledge thing, if anyone wants to understand, I hope this will help them. Again, I'm no way an expert. I'm not an expert. I am still learning, and whatever I know, I want to share with the rest of the world, and rest of the team, basically, who are all working on sites. Hope this gives you a bit of an idea of how the air handling unit works and how we program in the Visio. Any questions, do write to me in the comment section. And Urdu, Hindi, English, ये सब लैंग्वेजेस आई डू स्पीक. तो आपको कोई भी अगर डाउट है प्लीज़ बताइए हमें, और मैं जितना हो सके उतना आपको हेल्प करने की कोशिश करूँगा. Thank you so much for watching. Please like, share and subscribe so that I can continue to make more videos and share knowledge at the same time. Thank you.